8C, hypothesis testing for population means when you have a small sample and the population standard deviation is unknown. Now, just like when dealing with confidence intervals, when we have a small sample and the population standard deviation is unknown, we're going to have to use the t-distribution. But as we did with large samples where the population standard deviation was known, we have the ability to use rejection regions. Now, if you remember, I said that p-values don't work on the t-distribution table. And if you look at the way that table is designed, you'll realize you just don't have as many options with it. So p-values don't work, so we will use rejection regions. Which, in my opinion, is the easiest way to go anyway. It's consistent, and you'll find with the t-distribution table that it's really easy to find those values. Now, we will use the same processes as we did. We're still going to determine whether the claim is the null hypothesis or the alternative hypothesis, whether we have a right-tailed test, a left-tailed test, or a two-tailed test. We will still use a test statistic to come up with a standard score, but now, instead of using z, we'll use t is equal to x bar minus mu over s over the square root of n. So it doesn't really change much. Because we're using a t-distribution, our critical value will be t sub 0. Our rejection regions will have critical values with t sub 0. But the calculation, the only difference here is that we have s instead of sigma, so we can always use a sample standard deviation, but otherwise it comes out the same. And we do the same types of comparisons. So we might as well start right into a problem, and then we can see how we do this. So let me just pull a problem here. A cough drop manufacturer claims that the number of cough drops sold by the average pharmacy is 9,000 per day. You sample 12 pharmacies and find that the average number of cough drops sold per pharmacy is 8,700 with a standard deviation of 405. What statement can you make about the claim at a 0.02 level of significance? Okay, so let's pull some stuff out of this. A cough drop manufacturer claims that the number of cough drops sold by the average pharmacy is 9,000 per day. Average is equals. So they're claiming that mu is equal to 9,000 per day. You sample 12 pharmacies. N is equal to 12. And find that the average number of cough drops sold per pharmacy is 8,700, X bar. With a standard deviation of 405, S. What statement can you make about the claim at a 0.02 significance level? Alpha is equal to 0.02. Okay. So now that we've got that, we can start putting some stuff together. Well, first of all, the claim is that mu is equal to 9,000, equal, the claim is the null hypothesis because it includes equality. Therefore, the alternative hypothesis is that mu is not equal to 9,000. The alternative hypothesis points the way to tell us what type of test. Not equal to splits it into two pieces. We're going to deal with a two-tailed test. So we're going to have two tails. N is equal to 12. We have a small sample. We have the sample standard deviation, so we do not know the population standard deviation, so we have to use a t-distribution. Alpha is equal to 0.02, so since it's a Well, first of all, since we're using a t-distribution, we're going to have t sub 0 and negative t sub 0 for critical values. That 0.02 is going to get split between the two tails, so we have 0.0100 in that tail, and 0.01. Actually, I'm going to just leave it at 0.01 in both of those, and you'll see why in a moment. But we have 0.01 in both of those tails. So now I can go to my table, but wait a second, the t-distribution table requires degrees of freedom. Remember, degrees of freedom is equal to the sample size minus 1. So n is equal to 12, so degrees of freedom is 12 minus 1, or 11. So we can now look at this. Now, with the t-distribution, the top gives us upper tail probability. So this 0.01 that we have in the tails, we can look across the top to find 0.01. Then we go down to the row with the correct degrees of freedom, 11 degrees of freedom. So we come down and we get 11 degrees of freedom with 0.01 for our upper tail probability. We have 2.718. 2.718. The t-distribution will always give you positive values. So if you're dealing with the right-tailed, you're just going to take the area in the right tail and look at it as upper tail probability and give it a positive value. If you're looking at the area for the area in the left tail, you're going to use that as the upper tail probability and turn the resulting t-score into a negative value. So that's going to be negative 2.718. So now we have our critical values. Next step is to find our t-score. T is equal to x bar, 8,700, minus mu, the claim is 9,000, over s, 405, over the square root of n, which is 12. So we do our calculation. So 8,700 minus 9,000, 405 divided by the square root of 12. And we get a t-score of negative 2.57. And negative 2.5660011996, right? Continuing on. So rounding to two decimal places, negative 2.57. Now that we have that, we can put that into our distribution. Remember that center is 0. So if we have negative 2.57, 0, we get to negative 2.57 before we get to negative 2.71. The reason I always put the 0 in here is mainly because of the negative side. Because we have to remember that smaller negative numbers closer to 0, are the smaller numbers. So if we have negative 2.718, negative 2.57 is closer to 0, so it's actually on this side. People have a tendency to look at this and go, oh, negative 2.718, we have negative 2.57, well, that's less than that, and they put it on the left-hand side, which is not correct. The magnitude is less, but the number is actually greater. It's more positive. So we're not in the rejection region, so we fail to reject the null hypothesis. We have everything we need to make the final statement about the claim. At a 0.02 significance level, there is not sufficient evidence to reject the claim. So you see that when we're dealing with a small sample where the population standard deviation is unknown, the only real change to this is that we switch to a different table to get our critical values. The calculation from our test statistic to get our standardized value is essentially the same. It's still the sample mean minus the claim over the standard deviation divided by the square root of the sample size. Yeah, we call it the t-score now instead of the z-score, and we use the sample standard deviation always instead of the population standard deviation. But the calculation is done the same way. We get our critical value from a different table. We look at the upper tail probability and the degrees of freedom so we can get that value. If it's an upper tail, we leave it as positive. If it's a lower tail, we make it negative. But other than that, it's really the same process. And that's one of the things I love about hypothesis testing is once you know how to do it the first time, the other hypothesis testing that you do just follows the same process. Maybe you change to a different table, maybe you have to do a calculation slightly differently, but the method is all the same. And then the final statement always comes from the same three things. The significance level, whether you rejected the null hypothesis or failed to reject the null hypothesis, whether the claim was the null hypothesis or whether the claim was the alternative hypothesis. And that's how we do hypothesis testing for a population mean, where we have a small sample and the population standard deviation is unknown.